This video is about calculating convergence, which is a way to recover the value of a simple continued fraction. We'll give equations you can use to calculate convergence, and we'll work an example. Let's get started. Let's look at the equations. Each convergent is denoted p sub k over q sub k. We have some different equations for p sub k and q sub k, and which equation we use depends on the subscript k. We'll write one of the equations in this box. The equation for p sub k is p sub k equals p sub k minus 2 plus p sub k minus 1 times a sub k. And the equation for q sub k is just like it. Q sub k equals q sub k minus 2 plus q sub k minus 1 times a sub k. These equations for p and q work for any k, but the catch is we need the two previous values. We need p sub k minus 2 and we need p sub k minus 1. The same thing for q sub k. We have some equations that we can use to get started. In this box we have p sub 0 equals a sub 0 and q sub 0 equals 1. These equations work when k equals 0. And in this box we have p sub minus 1 equals 1 and q sub minus 1 equals 0. These work when k equals minus 1. Simple continued fractions don't really have a subscript k equals minus 1, so we'll put quotes around it. Don't worry about this, it's just a way to get the calculation started. Now we have an equation for k equals minus 1 and another for k equals 0. These two can be used to find the previous values that we need to get started with the equation that works for any k, starting with k equals 1. Let's do the example.
We'll calculate the convergence for this simple continued fraction. 4, 2, 1, 3, 1, 2. We'll make a table to keep track of the convergence as we calculate them. The top row has the subscript k. The other rows are for a, p, and q. P is the numerator of each convergent, and q is the denominator. For this example, k starts at minus 1 and goes to 5. Let's fill in the values of a sub k. There isn't a value of a when k equals minus 1, but starting with k equals 0, the values are 4, 2, 1, 3, 1, 2. Just to make sure you're following, these values of a are from the simple continued fraction. This 4, this 2, this 1, and so on.
We'll put a dash here for a when k equals minus 1, since there isn't a value. Now we're ready to start finding p and q for each k. We'll start with this equation for when k equals minus 1. P sub minus 1 equals 1, and q sub minus 1 equals 0. We can just write these in the table. Now we use this equation for when k equals 0. P sub 0 equals a sub 0. Here is the value of a sub 0. It's 4. So we write 4 in the spot for p sub 0. And q sub 0 is 1. So we just write 1 in the spot for q sub 0. We have the first convergent now. P over q is 4 over 1. Now that we have two values of p and q, we can start using this equation and continue using it for the remaining calculations. We'll get out a blackboard to show our work. Let's find p and q for when k equals 1, the p that will go here and the q that will go here. The generic equation for p is p sub k equals p sub k minus 2 plus p sub k minus 1 times a sub k. When k equals 1, this equation becomes p sub 1 equals p sub minus 1 plus p sub 0 times a sub 1. When we substitute values, p sub 1 equals 1, it's this one right here, the value of p sub minus 1, plus 4, it's this 4 right here, p sub 0, times 2, this 2 right here, a sub 1. 1 plus 4 times 2 equals 9, so we write 9 in our table in the spot for p sub 1. Now we'll do this for q. The generic equation is q sub k equals q sub k minus 2 plus q sub k minus 1 times a sub k. When k equals 1, q sub 1 equals q sub minus 1 plus q sub 0 times a sub 1. Can you figure out what the values are? Hit pause and give it a try. When we substitute values, q sub 1 equals 0 plus 1 times 2. This is the 0, q sub minus 1. This is the 1, q sub 0. And this is the 2, a sub 1. 0 plus 1 times 2 is 2, so we can put 2 in the spot for q sub 1. Our second convergent, when k equals 1, is 9 over 2. Let's move on. Next is k equals 2. P sub 2 equals 4 plus 9 times 1. Hit pause and see if you can identify where the 4, the 9, and the 1 come from. This is the 4, p sub 0, this is the 9, p sub 1, and this is the 1, a sub 2. 4 plus 9 times 1 equals 13, so we'll write 13 in our table. Q sub 2 equals 1 plus 2 times 1. This is the first one, q sub 0, this is the 2, q sub 1, and this is the second one, a sub 2. 1 plus 2 times 1 equals 3, which we can put in our table. The convergent when k equals 2 is 13 over 3. Next is k equals 3. Try to figure it out yourself. P sub 3 equals 9 plus 13 times 3, and q sub 3 equals 2 plus 3 times 3. In the calculation of p, this is the 9, p sub 1, this is the 13, p sub 2, and this is the 3, a sub 3. In the calculation of q, this is the 2, q sub 1, this is the first 3, q sub 2, and this is the second 3, a sub 3. 9 plus 13 times 3 equals 48, and 2 plus 3 times 3 equals 11. We can write these in our table. The convergent when k equals 3 is 48 over 11. Just two more. When k equals 4, p sub 4 equals 13 plus 48 times 1 equals 61, and q sub 4 equals 3 plus 11 times 1 equals 14. This is the 13, the 48, and the 1 that we used to calculate p, and this is the 3, the 11, and the 1 we used for q. We can write 61 and 14 in the table. The convergent is 61 over 14. Last one, k equals 5. P sub 5 equals 48 plus 61 times 2 equals 170. The font is different there because I messed up during recording, that's all. Anyway, q sub 5 equals 11 plus 14 times 2 equals 39. For p, this is where we got the 48, the 61, and the 2, and for q, this is where we got the 11, the 14, and the 2. We can write these results in the table. 170 over 39 is the last convergent. Now that we calculated this last convergent, we fully recovered the value of the simple continued fraction. We can write 4, 2, 1, 3, 1, 2 equals 170 over 39. Or we can write it longhand. 4 plus 1 over 2 plus 1 over 1 plus 1 over 3 plus 1 over 1 plus 1 over 2 equals 170 over 39. In summary, we saw equations we can use to calculate the convergence of a simple continued fraction, and we worked an example. That's all for now.